If we go ahead and continue on talking about stoichiometry in chapter number 14, again, looking at now volume and gases and applying it to stoichiometry. First one is going to be mass and gas volume. Again, the volume that we find is going to be at STP, and that's going to be key in what we're looking at here. Step number one for mass to volume stoichiometry, got to go back and write that balanced chemical equation. Number two, we have to convert that given mass to moles. Number three, write that mole to mole ratio. Remember, that mole to mole ratio comes from your balanced chemical equation. And finally, number four, we have to convert from moles back to that gas volume. And the question says, what volume of CO2 will be produced from 34.6 grams of C6H12O6 at STP? If I go through it again, start applying my steps. Again, step number one says that we have to balance that chemical equation. So by balancing that chemical equation, that's what I'm going to have. Now again, the question told me I have 34.6 grams of that, C6H12O6. And the question says, I want to know what volume, okay, volume will be in liters, at STP will be produced. And again, I'm going to be writing that STP up because, again, it's going to be key now, but on the next slide, again, you'll see, well, what if we're not at STP? So again, I go ahead and I start off 34.6 grams of C6H12O6. Again, molar volume, 1 mole of C6H12O6. I go ahead and I go to the periodic table. 6 times 12 for carbon, 12 times 1.01 for hydrogen, and oxygen, 6 times 16. When I do that, I get about 180.1 grams of C6H12O6. My balanced chemical equation, I find my mole to mole ratio. So 1 mole of C6H12O6 is going to be 6 moles of carbon dioxide. And then finally, it said that I had to go to a volume of carbon dioxide. And if you remember in the last chapter that we talked about, or how I made the chapters, I used part of chapter 14, we said 1 mole of any gas at STP, don't worry about looking anything up, 1 mole of any gas at STP is going to be 22.4 liters. Again, if you look at your units canceling out, this is what we'll be left with, is you'll be left with liters of carbon dioxide. Run that through your calculator and you'll end up with an answer of 25.8 liters of carbon dioxide at STP. You don't have to write at STP in your answers. I'm just doing that to show you what's going to be the difference between this problem and the next problem. So if you have a mass to volume stoichiometry, we're at STP, you just simply run the railroad tracks like you've been told or like you've learned. But as it says here, what if we're not at STP? It says if we're not at STP, well, one thing I want to do is I want to remind you of the type of problem we're doing. We're going from a mass to a volume. I want you to look where volume's listed. Volume's listed second. So if I continue reading, we have to use the combined gas law after or second we solve the stoichiometry problem. And again, if you remember what the combined gas law is, that's that pressure 1, volume 1, temperature 2 is pressure 2, volume 2, temperature 1. That will be done second after we run the normal stoichiometry that you've been told. And like it says there, convert second if we're not at STP. And again, when you look at this problem, it says what volume of chlorine gas at 30 degrees Celsius and 94.7 kPa. Again, you can tell that, again, we're not at those standard conditions. And it says will be needed to react completely with 16.4 grams of sodium bromide in a single replacement reaction. If we go ahead and go to the chemical equation. Going ahead and balancing my chemical equation, I go ahead and put a 2 there and a 2 there. Just as a reminder, 16.4 grams NaBr. Now, the question says I want to know how much chlorine gas is going to be needed. Okay, what volume of chlorine gas? But as a reminder to myself, I'm going to go ahead and put the conditions down here. 94.7 kPa, 30 degrees Celsius. Again, that's just to remind myself that I'm not at STP. So if I go ahead and start off just like normal, told you got to do this first. NABR, 1 mole of NABR. If I go ahead and add that up, that's about 102.9 grams NABR. Grams NABR, cancel grams NABR. Okay, mole to mole ratio, balanced equation. 2 moles of NABR is going to be 1 mole of Cl2. And then 1 mole of Cl2, 22.4 liters of Cl2. Now what I do is when I run that through, I get an answer of 1.79 liters at STP. 1.79 liters of Cl2. These are under the conditions of STP. What we're saying there is pressure 1, 101.325 kPa. What we're saying is temperature 1, 273 Kelvin. And what I just technically solved for here was volume 1. Well, you can see that we're not at these conditions. This right here, that's going to be my pressure 2. This right here is going to be my temperature 2. And essentially what I need to solve for is I need to solve for the volume under those conditions. So if I go ahead and go to that combined gas law, P1 V1 T2 is going to be equal to P2 V2 T1. And if I start plugging in 101.325 kPa, volume 1, that's what I just solved for, 1.79 liters. Temperature 2, okay, it's 30 degrees Celsius, but remind yourself, got to go to Kelvin, 303 Kelvin. That's going to be equal to pressure 2, 94.7 kPa. Volume 2, that's what I'm trying to solve for. And then temperature 1, that's my 273 Kelvin. So I'm going to take 101.325 multiplied by 1.79. I'm going to multiply it by 303. Technically, I'm going to end up dividing both sides by 94.7 kPa and 273 Kelvin. So I'm going to do that over here also. 94.7 kPa. Notice my kPa's will cancel. Divided by 273 Kelvin. Notice my Kelvins cancel. And what I will end up with for an answer, my volume 2 is going to be equal to 2.13 liters at conditions of 94.7 kPa, 30 degrees Celsius. So here's the answer I'm looking for. I had to convert second because this up here solves for standard conditions. I wasn't at standard conditions, so I had to use my combined gas law second because volume was listed second. Well, let's go ahead and look here. Volume to mass. Step number 1, as normal, balance the chemical equation. Number 2, convert that given volume to moles. And again, I'm going to tell you we're going to be at STP for starting off. Use that mole to mole ratio. And then convert from moles back to a mass. See, I don't need to do anything special with that mass because solids never change under different temperatures and different pressures. They remain constant. Look at this one here. It says what mass of KClO3 will be needed to produce 16.3 decimeters cubed. I hope you remember back. Decimeters cubed and liters are exactly the same thing. So if you want, just go ahead and cross that off. 16.3 decimeters cubed really is going to be 16.3 liters of oxygen gas at STP. Notice here's the key thing, at STP. We're doing normal conditions first. First thing I'm going to do is go ahead and balance my chemical equation. 2, 2, 3. Again, reminding myself I've got 16.3 liters of oxygen. Now, just to remind myself, this is STP. I don't have to do anything different with this problem. And the question said, well, how many grams of that? So we're going to start off with our given, 16.3 liters of O2. 1 mole of O2. Again, because this is at STP and this is a volume, I have to put liters down here, and 1 mole of any gas at STP is going to be 22.4 liters. Next step, mole to mole ratio. 3 moles and 2 moles. So my moles of O2 will go here just so they cancel. My moles of the KClO3 are going to go there. When I fill in, the 3's with the oxygen, the 2's with the KClO3. And then the last thing, 1 mole of KClO3. Because the question said grams or mass, I have to use the grams. Got to take a little extra step here. Got to look that up on the periodic table. When I look all of that up on the periodic table, I'll get about 122.6 grams of KClO3. Moles O2, cancel moles of O2, moles of KCl, moles of KClO3. Again, when I go ahead and multiply and divide, I get an answer of 59.5 grams of KClO3. Again, I'm not going to write down at STP because solids never change under different temperatures and pressures. So your answer, 59.5 grams of KClO3. What if we're not at STP? Okay. Again, I want to go back and I want to write up the type of problems that we're doing. Volume to mass. Notice where volume's listed. Volume is listed first, so what that means is we got to do something first. So it says here we're going to use that combined gas law before we solve the stoichiometry problem. And as it says there, we are going to end up converting first. In the complete combustion of butane, what mass of butane is needed to react completely with 33.7 liters of O2 at 89 kPa and 15 degrees Celsius? So if we go through and we start balancing this equation, we're going to put a 2 there, we'll go with a 13 there, we'll go with an 8 there, we'll go with a 10 there. Question told me that we've got 33.7 liters of this. Now, like I said, if you remember, it did not have standard conditions. So technically, this is my V1. The conditions that I gave you 89 kPa. That was my first pressure. And then the temperature was 15 degrees Celsius, but making sure that I go to Kelvin, 288 Kelvin. That's my first temperature. But as I said, we need to do the stoichiometry. We need to do the railroad tracks. Eventually, I have to use that 22.4 somewhere. And if I'm going to use that 22.4 somewhere, that means that I have to be in standard conditions of 101.325 kPa. I have to be in standard temperature of 273. And I've got to be able to use I have to be able to use that 22.4, and the only way I can use 22.4 is by figuring out a volume at standard conditions. So if we go ahead and start looking at filling in 89 kPa, 33.7 liters, using that second temperature, 273 Kelvin. What I'm going to do is I'm actually going to set up the division already. I'm going to divide it by 101.325 kPa, and I'm going to divide it by that first temperature, 288 Kelvin. That will give me my second volume, which that will give me an answer of 28.1 liters of oxygen at STP. I have to be able to use that or go to that so I can use that 22.4 when I go to the railroad tracks. Now this allows me to solve the problem. 28.1 liters of oxygen. Again, that's an STP number, so I can use this STP number. 22.4 liters of oxygen, that's 1 mole of oxygen. 13 moles of O2, and again the question said how much C4H10, how much of this over here is going to end up being needed. So 2 moles of C4H10, and since the question said go to grams, 1 mole of C4H10, I have to add all of that up on the periodic table. And when I add all of that up on the periodic table, I get about 58.1 grams. And when I run that through the calculator, I'll end up with an answer of 11.2 grams of C4H10. There's my answer. I had to convert first because, again, my volume was not at standard conditions.